Hello, everybody. Welcome to the Oceanic Robotics panel, in which we talk about the hidden world of robots. I think a lot of us think of robots, well, I guess we like to laugh at robots on land, typically falling over on their faces. I'm guilty about writing on that a good amount. But unbeknownst to most of us, out in the oceans for many years now, we have had very sophisticated robots swimming around collecting all manner of data for science. And today we are joined by a most excellent panel of scientists and roboticists to talk about this very cool science and how robots are going to save the planet undoubtedly. So I will let them introduce themselves.
Should I start?
Sure.
Thank you, Matt. And good morning, everyone. Are you all awake after losing an hour of sleep last night? Yeah? Maybe? Okay, yeah, me too. So I'm Jyotika Virmani. I'm an executive director at XPrize in prize operations and for the environment, and I run the Shell Ocean Discovery XPrize, which is a $7 million competition to get these robots, prototypes of some of the more advanced and sophisticated robots, to map the sea floor at a very high resolution, bring back images from the sea so that we have a sense of what's out there for the ocean discovery, and also to develop pioneering technology for what we're calling an underwater smart sniffer, and we'll go into that in a bit more detail. But I'm a physical oceanographer and a climate scientist by training. Thank you.
So I'm Jim Bellingham. I'm from Hole Oceanographic Institution. My original training is in physics, so I started out in superconductivity and made this left turn into the ocean sciences. I started building sort of marine robotics in the late 80s. I spent time at sea with them, design them, operate them, and I co-founded a company that builds them. So Bluefin Robotics was spun out of my old MIT lab back in the late 90s, and currently actually the entrepreneurial side of it is very near and dear to me, and we're currently in the process actually of setting up an accelerator for marine robots out at Woods Hole.
Okay, thanks. So I'm Jules Jaffe. I'm a research oceanographer at Scripps Institution of Oceanography in La Jolla. We're part of UCSD. I actually started life as a cryo-electron microscopist and barely missed winning a Nobel Prize 2 years ago, but found sailing was a lot more fun than sitting in a dark room and exploring our unknown parts of our planet. So we pretty much do anything that I think is fun and I can invent something. In the context of today, I'm going to talk about our underwater plankton mimic, talk about the Scripps' involvement in the Argo program, and we're also involved in a lot of different sensor stuff because our underwater robots need to see and hear and maybe even touch and smell, but we won't have time to talk about that today.
Okay, so what I'm going to do is ask each person kind of a question that pertains to their area of specialty, and then we'll open it up to a larger conversation, or scrum, depending on how we get into it. So, Jyotika, we'll maybe talk first about, I'd mentioned that we, of course, know robots on land as falling on their faces a lot. They're, of course, more than that. But oceanic robotics is a very diverse field in the form factors that all these robots are taking. But they don't live in a vacuum, right? So I was hoping you could talk about the way that ocean robotics is pulling in other areas of expertise on, from the 3D printing, things like that, things that we know about with robots on land. How is that seeping into the ocean with oceanic robotics?
Sure, yeah. So we're really living in a new age of technology and technology change and exponential change in technology. So you'd mentioned 3D printing. That's one really great example. But sensor technology that is based on biology, artificial intelligence, these are all things that we are beginning to see more and more frequently in other areas of our lives. Well, in fact, you all have some of this probably right at your fingertips, some of this great technology. And so what we're trying to do with this particular competition, the Ocean Discovery XPrize, is to really incentivize people to bring some of those changes into the field of marine robotics. So we have, for example, a final team that's 3D printed their technology, and what that does is make it a lot cheaper, which allows all of us better access to the deep sea. So we're seeing things like that. I know you've mentioned robots that fall over.
Those are my favorite.
By the way, you
yes,
shouldn't laugh too
those.
much because you know, they'll grow up and start laughing at us
true.
at some point. But so we're seeing not only in the field of robotics, though, but in the field of, say, medicine, doctors are now able to 3D print your individual organs. For heart transplant patients, they 3D print a heart, they practice on it to the point where they can now start to do bypasses, and you walk out a day or two later because it's nowhere near as invasive as it used to be, and the recovery is much faster. So there are some amazing, amazing shifts that are happening in other areas of our world and of our society, and we really want to pull that into the ocean world. And that's what this competition and all of our Ocean XPrize competitions are really encouraging and about.
Jim, at Woods, you have a pretty diverse array of oceanic robotics. One of my favorites are the ones that go into the Arctic. You cannot dream up a more impossibly difficult and deadly situation for a robot, which brings us to a really important point in oceanic robotics, which is autonomy. Right. So you need, as you can see up on the screen, one of these things under the ice. And as we were talking about earlier, it's actually much more difficult to pilot a robot under ice than it even is to do, say, a Mars rover. Maybe talk about the importance of autonomy here with these robots.
Yeah, so this was one of the things that I learned very quickly when I got into marine robotics, was that this was an area where even if you could do simple things with a robot, you could make a big difference. And the reason is because a lot of the things we take for granted in the terrestrial environment just go away when you pass underneath the ocean waves. So things that disappear are GPS. You know, GPS maybe penetrates a millimeter or so. And this is physics, right? So, you know, there's no clever invention that's going to make 3 gigahertz go through water because it's a conducting medium. The same thing with RF communication. So once it's below the waves, most of our robots are on their own. And if something happens, they've got to figure out how to deal with it on their own, or sort of deal with it, hopefully, in some way to get back. In the same token, we want them to do useful tasks in the underwater environment. And some of those tasks involve doing things that we think of as human tasks. So recognizing something unexpected, responding to it, sampling it in a way, perhaps triggering a water sample. You know, there's not a lot of water samples on the vehicle, so you want to use them well, for instance. And when you go under the ice, as is here, it becomes even harder because, you know, for us, our bail, you know, what we do when something goes wrong with our robot is we have it drop a drop weight and it pops to the surface, and and when it's on the surface, it can talk to the satellite network and it says, help, you know, come save me, or tell me what to do next more often. You know, when it's under ice, that doesn't work. You pop up under ice and you've probably lost the vehicle. So there it really forces you to come up with systems that can deal with these unexpected occurrences. You know, my friends who work in autonomous cars talk about, you know, sort of filling out all the edge cases, you know, before they're willing to sort of let humans operate it. We don't have that luxury. You know, we have to get our vehicles out there and working much faster. And so we have to be able to live with the edge cases. So for us, it's more a question of how do we give the robots the ability to deal with those unexpected circumstances.
And to be clear, Woods has a very good track record as far as not losing robots is concerned, but
yes.
An advanced robot like that, maybe tell us how much money you would lose if you did get it trapped under the ice.
Yeah, so these vehicles, so at Woods Hole Oceanographic, we have a range of labs that do underwater vehicles. And the high-end deep-sea mapping systems, if you fully kit them out, are probably about $10 million. And so that involves not just the robot, but all the support equipment. Of course, the mapping sonar alone is a large part of the cost. If you come back with a map, you want that map to be really accurate, right? Otherwise, why make it? Well, having a really accurate map requires very high-end navigation system, inertial navigation system. It probably requires aiding from the surface, from a surface vessel as well, because in the underwater environment, again, you know, we are absent a lot of the RF techniques. So these are things that really drive us towards more expensive systems. Right now, we're working really hard to make low-cost systems. And for us, low-cost means tens of thousands of dollars. And quite frankly, the tens of thousands of dollars vehicles are really not that capable yet, but it's early days. And you know, our picture is really, in many cases, rather than a single big, really highly capable system, what we would really like are fleets of lots of little vehicles. It actually turns out to be there's a whole mathematics behind this, but we can kind of prove that that is sort of the optimum, most efficient way to approach these sampling problems, assuming, of course, you have the low-power sensors to go with it. So,
Great. Jules, can you tell us about your tie first?
Oh, my tie. Right. So we study plankton. And one of the things we did was a three-dimensional scan of a 1 millimeter organism. And then we 3D printed it. So I thought it'd be kind of appropriate, being here in Texas, to have a bolo tie with a plankton on it. So thanks for the introduction.
Yeah, and speaking of plankton, maybe explain to the folks what plankton is, what a monumentally important organism this is in the ocean ecosystem, but also how you are using robots to explore how maybe those populations are changing in these kind of scary times of climate change.
Yeah, so thank you very much. So plankton actually means drifter, and these small organisms that can't swim very much play a fundamental role. I mean, the organism that I printed here is called a copepod, and it's actually the most numerous multicellular. Well, there's a worm that gives it some competition, but we ignore the land creatures. And so they are a fundamental part of the ecosystem. And so we have been studying plankton. So just to backtrack a little on what Jim said, our interest was in not only studying plankton, but in also creating swarms of miniature vehicles, which could sample this three-dimensional time-evolving environment. So oceanographers typically would, and years ago, we'd run a line and we'd get samples along that line. And you can't image the volume of the ocean. So you're subject to being part of that flow. Like you're driving along the highway and you're in this coordinate system where you're able to see the things around you. So years ago, I was asked by a friend of mine to come up with an idea that would allow us to track the trajectories of plankton in situ. And although I don't really have any background in robotics, we had some fun ideas, and we created this miniature autonomous float that allows itself to adjust its buoyancy. And we could track them underwater using a three-dimensional acoustic network. And we made some really wonderful discoveries close to shore, which were published in Nature Communications, major journal. And the idea was we could see the aggregation and disaggregation of the plankton underwater using this technology. And of course, one of the great advantages, well, here you're seeing now on the monitor how they get together. Well, you did see it. These are actually a bunch of dinoflagellates and diatoms. And so our interest is in, I guess my theme for the week is inform, educate, and inspire. So by inform, we mean try to figure out what's going on in the planet. Educate means, as a person at a institution that offers degrees, we want to train the next generation of people. And inspirationally, we want to inspire people to have better custodianship of the planet, but at the same time, a next generation of makers who can think about creating ocean instruments to satisfy some of the criteria that Jim talked about.
And congratulations to Jules for getting that through the TSA. On his way here.
Yeah, it does kind of look like a bomb, but they X-rayed it. I was like, you hand it to the guy, and he's like, if you're handing me this thing, you're probably not planning on blowing the plane up. So I was like, okay.
Good lesson to keep in mind.
Thank you.
So I wanted to open up the rest of the questions to everyone. And I think one of the things that really fascinates me about these early days of advanced robots is that we have begun speciating them. So in the same way that biological life has speciated over millions upon millions of years of evolution, we're doing the same thing with robots to fit them to certain niches. And I was hoping we could talk about, use this to talk about the variety of different oceanic robots that we have, how their form factors are fitted to different tasks. So like gliders you have that we saw earlier, looks like missiles, torpedoes going into water. You have things like Jules' devices here. How are those form factors actually taking shape, and maybe how does that almost mimic the way that species in a biological way adapt to a certain environment?
So I'll interject briefly. One of the revolutions that we're wondering about is called soft robotics. And if you look at the propulsion efficiencies of things like jellies, they're actually some of the most efficient organisms that propel themselves in the ocean. And so we've had some researchers at Scripps working with our wonderful engineering departments, robotics people up at UCSD, develop these flexible robots. And so that's kind of the future, I think, to some extent. And of course, if you're more gelatinous, you don't have to be worried about being crushed. So that's one speciation.
Yeah, I actually think of this in terms of scaling laws. So being a vehicle designer, one of the things that you do, and I think that people who design aircraft, ships, they're kind of familiar with this. You want to go long distances, it forces you to put more fuel or batteries in. That makes your vehicle larger. When your vehicle gets larger, it gets higher drag. When it gets higher drag, you have to, so you end up in this, sort of vicious spiral where your system gets bigger and bigger. And these scaling laws really help you understand sort of where in the design space, because your drag goes as the area of the vehicle, the amount of batteries goes as the volume, so that eventually they intersect, and eventually you get to a place where you get a vehicle that can go as far as you want it to go. But it turns out that depending on what you want to do, sort of thinking a bit out of the box drives you towards different types of design approaches. And Jyotika has a lot of, I think, great examples of sort of multi-platform systems where rather than one vehicle maps the area, and a lot of times in the ocean when we're mapping something that's changing. So it's kind of like taking a picture of the room. If my camera exposure is 30 seconds, it doesn't really help you resolve the people. It's got to be fast enough. And it's the same thing in the ocean. We're trying to get snapshots. And that drives you, if you have a single vehicle, to go very quickly. And we have this tyranny of drag. So every time we double our speed, the amount of power we need to drive our platform through the water goes up by factor 8. That really is painful, right? On the other hand, if I put two vehicles in the water, I can go twice as fast with each of them going the same speed and only use twice as much energy. So that's where the scaling laws start really working to our favor. So I think and we see this in nature. Mother Nature makes things that are really big. Whales, for the most part, don't really go that fast. They go about, kind of 3 knots-ish. Type speeds, 1.5 meters a second. Or other times, Mother Nature uses lots and lots of little stuff, right? All the way down to really small things that float, like, jewels, which are abundant, right? They're everywhere, but they tend to cluster in certain places at thermoclines and things like that. So there's an enormous amount to learn from nature. As a matter of fact, there's a whole field of study. It affected my sleep habits for several months when I discovered this field called allometric scaling, which is all about understanding how attributes of organisms scale as the organism gets bigger and smaller. And there are design laws that work across orders of magnitude with organisms, which to a vehicle designer look really familiar.
And yeah, in this competition, we've seen some very outside the box thinking, as you referred to, different form factors. Early on in the competition, there was a team that looked at how bees worked. So the idea there was that there would be a lot of small worker bees that would go out and map the seafloor, and they'd come back to a hive that was in the ocean, and that would gather the data and transmit it back and then go out again and continue the work. One of our final teams, so normally when we map the seafloor, the technology, first of all, it's launched from a ship. And it can cost up to $120,000 a day for some of these high-end vessels to go out into the ocean and map. And if you're sailing for 10 days, you've already lost 1 million, 1.2 million. So it's a hugely expensive enterprise, in addition to the technology that Jim was referring to, where the device itself can cost $10 million. So we incentivize teams to remove the ships. So all of the technology is launched from the coast. So one of the final teams, oh, by the way, the picture here, this is an unmanned vessel. It can be remote controlled, or if you imagine the NASA mission control banks of computers, you could sit here and have mission control, and it can be hundreds of kilometers offshore, and you can control it and maneuver it remotely. And it will automatically deploy the device that goes underwater and maps the seafloor and recover it with no humans out there at sea. So that's one piece. The other one, another team of ours, is using a completely different approach to mapping. So most mapping technology is done in a lawnmower pattern. This team has designed, and I think there's maybe a picture of it. It's a vertical pod that goes up and down. I think it's the next picture. It goes up and down in the water column. And you see it actually, the orange thing and the black thing, that's just one of them. The idea there is that the surface vehicle will have a number of these, and as it goes down, instead of mapping it horizontally, it takes a circular map, and then it bounces on the sea floor and keeps collecting circular maps, and then in post-processing, they get stitched together. But as the first one's going down, the surface vehicle will move to the next station, drop the next one down, so that can start, and then the next one, and then the surface vehicle will come back around and pick up the first one, which has done a section, and recharge as it sails to the next point to pick up. So you actually gather maps at high resolution much faster than we've been able to. So this team was basing it on the ant world. So to go
They
back
don't live
to,
underwater, though.
They don't. Well, actually, some of them build bridges across water.
That counts.
Right.
Yeah.
So if you've ever seen them, there's like thousands and thousands of ants, and they build a bridge. And the idea is, if one falls off, it's okay. You've not lost the bridge. So in this case, their idea, again with the swarm technology approach, is if something happens to one, it's okay because you still get most of what you need, and the mission is accomplished. So teams really use different nature, ideas from nature to try and think outside the box.
But these actually require things that we're actually not very good at underwater. I mean, communications is a great example. If you have vehicles that are cooperating, you'd really like them to be able to talk to each other. Well, our RF network doesn't work down there. So as we were,
RF
talking about a little
frequency?
bit. Yeah, our radio waves don't penetrate there. So, we have to develop these acoustic and even sometimes optical methods. As, we were talking about it, we have better communication with robots on the surface of Mars than we do on the seafloor. A lot better, like zero communication with robots, robots on the seafloor. And so those are the types of things that we really, there's this whole infrastructure, right, that we're kind of working on. It's not just the platform, and it's not just the autonomy. It's all of these other pieces, including navigation and comms, and the logistic support from surface vessels, and energy scavenging from the wind and waves, which all begin to factor into it.
I think actually underwater communications is probably the biggest issue that we face in really having full access to the deep sea. So first of all, if anyone has a great idea to solve that, please come up and see me afterwards. I think the surface communication piece will be solved in the next few years with Starlink, which is a SpaceX endeavor, has just got permission last year to launch another 7,000 satellites. So we're looking at, global communication. Even 5 years ago, I was sailing in the Pacific for the Wendy Schmidt Ocean Health XPrize, and we could only send emails if we were facing west. So that's how poor our surface communication from the ocean was just 5 years ago.
Why west?
That's the way the satellite.
Yeah, satellite was probably blocked by the stack.
Well, they wanted to go back to work, and no more email for you.
Yeah, I know, it's
We're not
great.
pointing west.
In a way, it was great because you're working, but you can only email if you're facing west. It's not your fault. Those days will be days of the past, though.
Yeah.
Well, one form of speciation would be vehicles that float and go along with currents versus vehicles that are self-propelled.
Yeah.
And they're each measuring, they have different, energy profiles. I mean, the floaters can last a long time, and many of them are meant to be in the same reference frame as we are, as the organisms around them. Going up and down in the ocean we change our buoyancy, so that's not very expensive. But in terms of your question, I think that's an interesting distinction to make.
And one more point on this is that actually there's a large range of sizes as well. So we see this, but even in mapping the seafloor, I wish there was a way we could get all of them. One is almost 40 feet in length, all the way down to something that is maybe just 1.5 times the name tag here. even I could carry. I'm not sure what TSA would think of it, but anyway, so there's huge range in sizes as well.
Well, and we also know, and I don't know much about it, that the Navy is developing extremely large autonomous vehicles, basically.
As they are wont to do, yeah. So we have been talking a lot about some forward-looking robotics, but we have had robots in the ocean for a very long time now. I think this is a good opportunity to talk about what exactly kinds of data they are collecting. And I think probably most importantly for our species or the planet as a whole is climate change. So maybe in that context, with Argo and things like that, what kind of data have these robots been collecting that will help us not destroy ourselves, ideally?
Well, I'm not sure if they're going to help us not destroy ourselves, but we believe that knowledge of the changes that are occurring in the environment are important to motivate us to make changes in our lifestyle and perhaps our economic machines. The Argo system we're very proud of Argo at Scripps. Dean Remick is one of our scientists, was the lead investigator. And I just wanted the story of Argo and how science works. It's a cooperative endeavor. And in 1999, there was a meeting called Oceanobs. And there's actually going to be another one this year. And a bunch of scientists got together and they said to themselves, look, the way we study the ocean is we take a ship and we drive it across the sea and we basically stick something down and we do these vertical profiles. And 35K or 120K a day, that can be a very expensive thing. But they had already prototyped some of these autonomous floats, like the Argo vehicle, here, and they decided, well, we could put thousands of them all over the world, and we could start to do more global mapping. So the interest in that partly is because you may be familiar that 90% of the greenhouse warming is sequestered in the ocean. So we want to critically understand, not just as physicists, what the currents are doing and where things are going, but how that is affecting the planet itself. And that really requires a global mechanism for studying those kinds of things. And so the Argo system you're seeing here, you may recognize that as our home. And you're seeing now, today, we have 4,000 Argo vehicles in the ocean, producing huge amounts of data, which are being assimilated into physical models. And the temperature there is being expressed in color. So a few milestones. We had our 2 millionth Argo vertical profile recently. And we are developing new kinds of Argos. One of the kinds is a biogeochemical Argo, which allows us to look at nutrients and also some of the other things like fluorescence, to start to look at the chemistry of the ocean and the biology of the ocean, just not how things are pushed around. So I think I was informed this morning that there are 338 of the biogeochemical Argos out there as of today. And the other thing that's really kind of cool is that when we look at the global circulation of the ocean, a lot of times the currents are not moving just horizontally, but they're actually moving vertically as well. And so we'd like to know how much of that heat is being transferred into the deep ocean. Critically important. And so we've developed now, by community consensus, these deep Argos. There's one there, a little cylinder capable, I think, of going to 6,000 meters. But the other thing I want to highlight about the Argo story is that this is truly an international collaboration. There's a Japanese Argo, and there's an Italian Argo, maybe Argonetti. And as scientists, we love the ability to talk to people about what we do and cross those cultural boundaries. And I think it's important to keep a perspective that the planetary changes are global. And Argo is really a wonderful way to start to understand what's going on, but there's much more to do as well.
I think it's actually, sorry?
No, I was going to add an anecdote to that, but I'll let you.
Well, so I was just going to say, as a physicist, right, who came to oceanography, I remember sort of thinking, seawater's simple. It's a bunch of water molecules, there's some salt mixed in. And by and large, if you were to read oceanography texts from the 20th century, that's by and large what the story is. It's about understanding how the ocean circulates, how it transports heat. And that is a story of temperature, salt, and heat, and of course pressure, right? The ocean being a very deep place. The average depth of the ocean is about 3.5 kilometers. Deepest part of the ocean is about 11 kilometers. We have sort of shallow water near the coast, but most of it is deep. And understanding how it performs and how fine that structure is has been a story that really has evolved over really centuries, right? I mean, Benjamin Franklin really was the one who understood the Gulf Stream for what it was. And now, we have things like satellites that tell us that the structure of motion in the ocean is much finer. But now, in the 21st century, we're beginning to ask questions about the chemical makeup of the ocean and the biological makeup of the ocean. And we realize that the ocean is, when you take that drop of water, it's not just salt and H2O molecules. There's literally tens or hundreds of thousands of little organisms in there, each of which is a chemical factory. And it's actually literally determining the chemical makeup of the ocean. If you took all the organisms out, you'd have a completely different ocean, a completely different chemistry. So they completely, it's literally a living fabric there. And the tools to measure that are really only becoming available. So as we move forward in this century, that's going to be the exciting story. I mean, that is probably the least poorly understood part of the climate system, right? Is all those little biological pieces of it, those little microscopic organisms that are doing all of this work of, taking carbon dioxide and, breaking it up and putting it back together again. And, it's still a highly unexplored, not understood environment. And robots are kind of the key tools which allow us to then penetrate to that undersea environment and begin to tease some of these mysteries out.
So there's 1 million bacteria in every milliliter of water, something like 10,000 phytoplankton. These guys are only about 1 per liter, but there's 1 per, 100 cubic meters in this room. So it's
I got it. I'll laugh at your jokes, Jules.
Thank
It's
you.
okay. See? I was actually going to add an anecdotal, an additional piece to the Argo story there.
Sure, great.
So we awarded the Wendy Schmidt Ocean Health XPrize almost about 5 years ago, actually, and that was a competition to develop pH sensors for the ocean. So pH we need to measure because it gives us an indication of ocean acidification. So we know the climate's changing, but the ocean is responding. And the way we used to measure pH is to sail out, very expensive, get a water sample, bring it back to the lab, and measure it. So as of 2015, we have high-quality lab level sensors that we can leave out there. So one of our winning teams from that competition actually gave their $250,000 winnings to the Argo program so that we could get pH sensors out into the ocean, around the Southern Ocean especially, which is a very valuable ecosystem, to make those, to really start to build up that base of what is going out, the baseline of what the chemical changes are as in response to climate change. So really, and that actually also shows that it's not just about the money at the end of the day for the teams who enter these competitions. It's about the challenge and achieving a change and an impact.
Yeah, so the pH is really important for organisms that use calcium carbonate to form shells. And there are stories about a very interesting organism called pteropod now, which is starting to be unable to create its shell based on the acidification of the ocean. So kind of a sad story, but important to measure pH and understand how it affects the climate.
So we have climate change. The robots are helping us parse that, given how monumentally important the ocean is for understanding climate change. But I was hoping to talk about some other things that robots might help us save the world. We were talking about illegal fishing earlier, maybe some changing in shipping up north. Let's talk about getting away from the most epic giant problem our species has ever faced into these more granular problems that our species now face. What else are these robots doing out there?
So one up-and-coming example is around that illegal fishing. So one of the ocean, first of all, is vast. And it's easy to say that, but to actually realize it is very difficult. It is so huge. And so we have these vast marine protected areas where illegal fishing does occur. But we have no way of actually monitoring it. It's fine having satellites, but we're looking at small scale. And the issue in actually prosecuting someone who is doing this activity is you have to have proof. And by the time someone knows something's going on and they've got out to that location, people have left. So using sophisticated acoustics, you can listen in the water. You can hear when the noise changes and something funny is going on. And so now we're starting to see these autonomous platforms that get triggered by shifting acoustics that will be able to hone in on activity and actually then trigger a camera system so that you can start to take gather proof of who is doing this so that there is some evidence for prosecution, which is a really clever way of integrating a number of different pieces of technology together in a ocean robot form to help us with this issue.
Yeah, so they're used for a whole host of things. So seafloor mapping. We go look at Google Earth or the Bing equivalent of it. You can get the spectacular imagery of the landmass. Underwater that all goes away. There's very few places in the ocean where we have decent maps. And as a matter of fact, if you're up in the Arctic, you might be navigating, and you're in a ship up there, you might actually be navigating using charts that were last created when people were literally lowering lead weights into the water and measuring how long the line was. So pretty antiquated maps. So now we have these systems which can get very close to the seafloor and give us very high resolution maps. And that really transforms how we think about the deep sea environment. It changes how we think about earthquakes. We can see the evidence of fault lines in the undersea environment, which tell us something about, for example, how big the earthquakes might be. It's an environment where we don't really have many seismometers. We have almost no seismometers, so we don't understand tectonics in the ocean very well. And it lets us also, the same tools apply to many other problems. The military uses them for finding mines. And it was told we used them for finding the Air France that was lost in the middle of the Atlantic. So I don't know if you remember. There were 4 searches, and the last search was done with AUVs, and the AUVs actually found it quite quickly. We're also using them in the Arctic as there's more human activity up there. The risks of accidents up there increases, but there's no logistical capability to respond to an accident should one occur. And so we have a program which is developing a robotic capability for the Coast Guard, which is sort of a first response AUV that they could take out in a helicopter and leave behind to sort of map out an oil spill should some big cruise liner or something run aground up there and have an oil spill. So they're increasingly tools that we use and we start filling in. And right now we use them in conjunction with humans, but as they get more capable and can last longer, we increasingly send them to sea on their own and just talk to them via satellite links.
Yeah, I guess we could talk a little bit about gliders, which are really miraculous technology. It turns out that if you just adjust your buoyancy and you change your wing angle, you can use that to propel yourself forward. So we have gliders based at Scripps now that are going out for 3 months or so and coming back and giving us amazing information. A colleague of mine invented one to look at plankton, much like this one. And I think the gliders are a wonderful example of autonomy and how we can get pervasive information. But the other thing that I find really interesting is, as a person mostly interested in biology, is the need to sample adaptively. So a lot of times there are these ocean fronts as opposed to geology where things change, and we're seeing changes in those structures of those fronts as the planet's ecology is transformed. And the autonomous capability to adaptively sample these fronts where there's a plethora of biological activity, I think we'll see more and more about that, because it turns out the ocean is not full of things that are all homogeneously spread out. but in fact is extremely patchy. And so the ability to find those patches, hone in on them, and sample them with adequate resolution to characterize species and the physics, I think will be a miraculous change in the way we study marine life in the ocean.
Can I just, I'm going to pick up on some of the mapping stuff that Jim talked about. First of all, the current estimate is that it would take over $3 billion to map our ocean floor to a high resolution. The map that you see on Google Ocean is on average about 1 kilometer resolution, which means that from here to 1 kilometer away, you would see nothing. It's all the same level, no buildings, trees, nothing. That's currently our ability to see what's down there. So, it's estimated that there's a few million shipwrecks down there. So insights into our own human history. They say, the ocean is the world's largest museum. We just don't have access to it yet. So that's one piece of the mapping puzzle. And you talked about plane wrecks, right? So when they were looking for the Malaysian airline that went down in 2012, now I think it was, they didn't find it, but they found 2 new volcanoes, one of which is bigger than Mount Vesuvius. So this is only 2012. This is not that long ago, where we're discovering on our own planet volcanoes that size. So that's really, really shows how poor. And that was one of the triggers, for this competition. But I mentioned earlier the NOAA Bonus Prize, which is an underwater smart sniffer. So that's, and that's a nickname, by the way, technology that can detect a biological or chemical signal underwater and autonomously track it to the source. So the one example of a long-term use for the technology that's coming out now between the automation, the launching from shore, and that smart sniffer is if a plane goes down, instead of sending people on search and rescue missions, you send the robots out to do that search and rescue capability and to find if it's a plane or a ship, or even looking for biological hotspots or hydrothermal vents instead of spending and risking human lives at sea. Let's get the robots to do that work initially, and then we can go out and dig deeper.
Yeah, well, if you look at the search technologies, I was actually on CNN a bunch of times and I unfortunately told the producer that I thought the way they were trying to find the shipwreck was inadequate, and then was confronted in daytime TV with, why did you tell our producer they were doing things lame? But the answer is that they're towing one hydrophone, which can hear something maybe 1 kilometer or 2 kilometers away in this vast ocean, where you could imagine swarms of underwater vehicles that had multiple hydrophones that were, because that black box only goes for, 30 days or something like that. So the capability for autonomous search using autonomous vehicles, I think, will miraculously change our abilities to find things in the ocean that we're interested in finding.
We're running a little bit low on time. Wanted to open up for questions after this one last question, which is sharks, which is more of a statement, I
Everyone
guess.
loves
But
sharks, yeah.
the design challenges when it comes to creating robots for the most inhospitable place on the planet, if you're going several thousand meters deep. But what kind of challenges do you find besides sharks chewing on your devices when you are designing these things?
Yeah, so I think that, well, first of all, sharks are sort of an advanced level problem. Sort of you get to encounter a shark when your vehicle really works and it's out there for a long time, and it turns out that there are things that go bump in the night out there a lot. So if you have a vehicle that's out there for weeks at a time and you look at the data set really carefully, you'll see that things are jostling the vehicle. The more typical problems, of course, we deal with pressure, right? The pressure of the ocean, it is basically equivalent to 1 atmosphere pressure for every 10 meters you go down. You can imagine 11 kilometers, that's a lot of atmospheres down at that deeper part of the ocean. And we have a lot of clever ways of dealing with that. You know, one is you make things which can sustain, which can make a 1 atmosphere container, so make it safe for all of your electronics inside. But we actually also are pretty good at figuring out which electronics will survive at those really high pressures. So it turns out a lot of the electronics will. So we make something that we call pressure compensated electronics to operate things without a pressure vessel. And that lets us make a smaller, cheaper vehicle. Communications, I think we've already talked about. Power is a really big deal for us. And, you know, we're sort of, you know, the amount of money that goes into batteries, you know, that's put into batteries by the consumer electronics and, you know, the automotive industries is enormous. We're never going to match that. So we sort of ride on their coattails. On the other hand, we've gotten very good at figuring out how to use our energy very efficiently. And what's more, it turns out that the energy is actually a high energy environment out there. There's waves, there's wind, there's thermal structure in the ocean, and all of those are sources of energy which various clever roboticists have figured out ways to extract that. So there are vehicles that are wave powered. There are vehicles that sail. There are vehicles that extract, there aren't vehicles that extract energy from, there's actually biopotential in the seafloor, and you can extract electricity from that, but those things actually tend to sit there. So there's a range of challenges, but then there's also sort of a set of opportunities as well that are unique to the ocean environment.
Well, but let me be a bit cynical here.
Ah.
I am not convinced, as someone who studies biology, that we are entirely non-invasive. In fact, many times pictures of your vehicles show little remoras following them around.
Yeah.
Sometimes the vehicles are noisy. And I challenge us to think of a next generation that would be less invasive to allow us to sample the environment in a way that we could convince ourselves. As the classic example, Jim was at Mabari for many years, was your ROVs.
Yeah.
And you found that basically the pneumatic
Yep.
and the other ones saw different creatures,
You're
basically.
absolutely right. I mean, they were both acoustic and optical signatures, right? I mean, you have brilliant lights that you're taking down there, and those, you know, attract one set of organisms and scare off another. And then the acoustics also. They're not as loud as a ship, right? So, I mean, just as an environmental problem, we're like 1,000,000 times less noisy than the stuff that's out there plying the ocean every day. But we're still loud enough that we affect what organisms might be around us. And as a matter of fact, AUVs have been used to test this. So there are fisheries vessels that are used to set survey quotas. And so there's questions about whether or not they actually really report the right number of fish out there. So people have used AUVs to do an advanced survey, which they then compare with the ship survey, and found that, in fact, the ship does a pretty good job of scaring things away as well.
Exactly.
So yeah, so these are really, yeah,
Just
these are
thinking
And I think-
futuristically,
Well, and I think
that's one of the things we should think about.
some of that is, we can already see the footprint of some of that, Jules. I reflect the mirror back at you with that with your the eel, the robot eel that you
Okay,
showed.
sure.
So that's not as invasive as a hard structure would be.
Yeah.
But also eDNA. So eDNA is a way of taking water, and again, this is relatively nascent technology, but it's on its way, is to take a water sample and then through the DNA that's left by something that swam through it to try and figure out what was in that water sample instead of actually having something in the water at that time. And they're starting to compare that to traditional fish count methods to see how closely those numbers match up. So it's a different way of approaching, and I think we're starting to see that shift coming where we're not quite so invasive.
So I just want to jump in. You both have talked about Argo. That's the most populous, number of robots. There's the largest number of robots in the ocean. And I just want to be clear that even with 4,000 of those in the ocean, that's like 2 in an area the size of the state of California. So, we have a long way to go before.
That's true.
Okay, I
Before
think
we're well
that's
sampled,
a
yeah.
good positive way to end it instead of the deep cynicism of climate change. Robots are fun. But I wanted to leave some time for questions, and Jyotika has bribes.
I do. You get a bag for whoever asks a question for the first 4 questions.
That is bribery, and we're not
XPrize.
afraid to say it. If anybody has questions, you can head to a microphone or just yell it loud. I'll kind of repeat the question for people who didn't hear it. He's wondering about the level of autonomy that you need, given that there are satellites and things in the sky.
Yeah, so this is a great question, and of course, we don't actually, when we design observing systems, we use everything we can. So satellites are absolutely a part of it. However, satellites really, if you look for the sea surface temperature measurements, which are, for example, a particularly useful product, that's only telling you about the very surface of the ocean. And the ocean is highly structured. There's a great deal of variability in the top 10 meters or 50 meters or 100 meters, depending on which part of the ocean you're in. And it may be very different. The nutrients are different, the chemistry is different, the biology is different, just a little bit down below that. So unless you have the vertical structure, you actually don't know how to interpret those satellite images. Don't get me wrong, those satellite images, and by the way, satellites are really expensive, right? So that $3 billion that Jyotika mentioned for mapping the ocean, that's actually, if you look at some of our more sophisticated satellite programs, it's actually not that far. That's not that far off of that. But you're right. I mean, you want to throw everything into it. We have other surface tools which give us, for example, surface currents in the nearshore environment. Also, HF, they're basically high-frequency radar techniques. Those are extremely powerful and useful as well. But if you want to understand the undersea environment, you actually usually have to take your sensor into it, and you have to make the measurement there, or you don't know, particularly with... Yeah, you bob back up and you can send it back, but let's say you're at 6 kilometers water depth. A typical fast-moving vehicle might travel at 30 centimeters a second vertically. So how long does that take you to get to the surface to send that information back and come back down? You're on your own when you're kind of down there. And if you're under ice, you're really on your own. So yeah, the autonomy, you want to construct a practical system, so you want to minimize, in a way, the amount of complexity you built into it. And it tends to be that a lot of the complexity comes from contingency planning, which is often safety and failure driven. And so that drives actually probably the most vibrant part of the autonomy research, actually, which tends to be kind of the comparatively boring piece that revolves around reliability. Even though kind of the flashy stuff is all sort of adapting and doing cool things in the ocean. The other thing actually has a higher impact. But yeah, good question.
Sir in the front.
So, what I love, I think a lot of people love, is that NASA has done a really great job of providing pictures from the rovers, and getting on Instagram and engaging people, kind of putting them into orbit, right?
Yeah.
Now, do you imagine these robots
I can take
being used to engage people in the sci-fi and the deep ocean?
Yes.
Okay, can I repeat the question? So he's asking, NASA has really good social media team with great images
Yeah, how
from
much did
other
Jyotika
planets.
pay you to ask that question?
Gonna get back.
They have great images, they have great PR. Can we do the same for oceanic robotics?
Yeah. So one of, not just through this competition, but in general, technology is getting cheaper and easier to use, etc. One of the areas that we would like to see progress and a push in is something like deep sea ecotourism. So if you combine the imagery that we're now getting, we can get 360 cameras down there, along with things like virtual reality, which has come a long way in the last couple of years. You can have a completely different experience of the ocean than we've had ever before. So that's one area that we're certainly looking at. The other thing we did as part of this was to look at how can we inspire people about the ocean the same way that we all look up into the stars and get inspired. So we did some work between comparing, because at XPrize, of course, we have space XPrizes as well as the ocean ones, is to look at how does the space community talk about space versus how does the ocean community talk about oceans. And actually, I'm going to talk about this in a panel tomorrow, so if anyone's interested, New Age of Ocean Exploration, just a shameless plug there. But there are some actual differences in how we communicate, the two groupings communicate. So the space industry, I mean, NASA has done a fantastic job with their images and really making it accessible to the public. So for example, Pluto, when they finally got, a photo of a rock that's so far away that we probably will never get to personally, at least not in our lifetimes. And they had these memes of, first of all, they named it Pluto, which was genius because Disney already has that character. But secondly, those little heart shapes and Death Star memes and all this kind of fun stuff. And I think in the ocean community, we tend to be a little more serious, so maybe we need to lighten up a bit. Another difference is, and perhaps real, this is real, is that we talk a lot in the ocean community about the negative aspects. So we're polluting things, we're killing things, it's the end. And NASA's out there going, we're going to find life, and this is a mission, this is great. So there's a whole body of work that we started on that track to really try and change that narrative as well.
So there's, the question of accessibility, and I was at a great meeting at MIT a few months ago called All Hands on Deck, and there's a platform called OpenROV where people can buy for a couple of $1,000s an underwater robot and swim it around. And I think the idea of having access to that environment in real time with your very own robot creates tremendous opportunities to get the public excited. But for sure, we have nowhere near the outreach budget of NASA, and nobody knows how to change that, basically.
Sorry.
Go ahead.
I was going to add that I reported a story a couple of years ago at the Monterey Bay Aquarium Research Institute. They had taken their data mapping the seafloor and piped it into a VR headset. So you put it on, and you can actually fly around the seafloor, which I think is, you're getting so much data from these robots that you can create these sort of systems that would be very difficult to do with a Mars rover. So it's really immersive way to see the seafloor for yourself.
One thing we did actually as a follow-on competition after the Ocean Health XPrize is an app challenge, so the Big Ocean Button Challenge. And one of the winning apps was along those lines, something like, I don't know if you've got the Star app where you can just point it at the night sky and it tells you what planet's there and what's there, is to point it when you go to the beach and it removes the ocean so you can actually see what the bathymetry is like. Or if you're somewhere else and you want to see, the Monterey Canyon, for example, and we're sitting here, you can just put it into the app. And so, but we obviously need the data of that resolution as well. So it kind of feeds into one on top of the other in that way.
Yeah. We'll do one more question, and then we'll probably wrap it up. Yeah, go ahead.
Dr. Bellingham, you mentioned at the beginning an accelerator for robotics. A little bit more about that.
Sure. So one of the things that
Do you want to please repeat the question?
Sure. So I mentioned in my introductory comments that we're starting a marine accelerator. Actually, we call it Disruptor Works out in Cape Cod. And this is a new initiative of ours. We've got our initial funding from the state, and now we're beginning to bring in some impact investors on the project. And here's sort of the capsule idea, is that there's, as Jyotika mentioned and as Jules mentioned, there's a lot of really interesting ideas out there that are coming in from outside of the marine robotics and outside of the oceanographic community. And so people are bringing to bear additive manufacturing, new power sources. There's all kinds of clever ideas out there. The problem is that getting things to work in the ocean environment is really hard. And those of us who have done it have learned lessons over a couple of decades. So when Jules gets his robot to work there, which looks like you would think, oh, well, he built that and it went out and worked the first time. Well,
10 years.
Yeah. See, so this is a classic story in the marine environment, is sort of 10 years from the back of the envelope to something that works. We want to speed that up. And we want to speed that up through a variety of methods. We want to provide facilities to people that mean they don't have to test their stuff at sea. They can test it in a nice, safe environment where they can tweak things. We want to provide access to people who've had experience in seagoing and testing seagoing systems. And we're creating offshore test environments as well, where the communications and navigation things, which you would have to set up yourself, are put in place. So, you know, if anyone out here is a marine robotics entrepreneur or wannabe marine robotics entrepreneur, we hold a entrepreneurs forum every summer. This summer, I think it's the July 17 and 18, and we bring the community together, and it's only about, as a matter of fact, this year we're calling it a rising tide. It's all about enabling the marine robotics community to get faster at bringing its capabilities to market, because we think ultimately, I mean, we come up with all kinds of crazy ideas and we demonstrate it, and that's great, but it's not really going to have impact until everyone can get it, and everyone can get it at a reasonable cost. And so that's what we want to enable.
Okay, we're going to have to call it, unfortunately. Are you going to be around after this to take extra questions? They will be around if you want to get them offline. Please give our panelists a round of applause.
Thank you.